Blackbody radiation and quantized energy.
So, at the turn of the century, our understanding of the physical world was changing rapidly. The electron was discovered. There was evidence that the atom, which had been considered to be the tiniest particle of matter, actually had an internal structure. Cathode rays were found out to be particles. In fact, they were electrons. And the distinction of ray-like properties, in other words, light, and solid matter, such as particles, started to blur. Next, the very nature of light was to be challenged. All objects emit electromagnetic radiation. This radiation depends on their temperature, and as such is called thermal radiation. We're going to define what a black body is. A black body absorbs all electromagnetic radiation, such as light, that falls on it. No light is reflected or transmitted, so the object appears totally black when it is cold, hence the name black body. However, an interesting effect occurs when you heat these black bodies. They will emit a temperature-dependent spectrum, and it is called blackbody radiation. At normal temperatures, for example, room temperature, 30 degrees Celsius, we're not aware of this radiation. But as objects get hotter, we can feel the radiation, the infrared radiation or heat. So we have a couple examples over here. Here's a light, and you can see as it warms up, that's what's happening here. It's been turned on, it's warming up, and you can see it's glowing red. Okay? Now, at still hotter temperatures, this same object is going to glow white. Okay, white hot, such as the filament in this light bulb. So it started out red, keeps heating up, and we get it to a white color. The previous slide showed how an object changed color as it got warmer. Many people would be happy with that. However, Wilhelm Wien did many experiments, observed what happened. He actually came up with an equation. Again, this was not derived from any theory or thinking about it. He measured. So he found out that the color of light, which is lambda, the wavelength of light will tell you its color, times the temperature, where the temperature is given in Kelvin. When you multiply these two numbers together, you get the maximum, lambda maximum, times the temperature is equal to 0.28978 times 10 to the negative 2 meters Kelvin. That's what this unit is here. It's meters Kelvin. This is called Veers Displacement Law, and basically it shows that the higher the temperature, the shorter the wavelength of the peak color of the light. Right? We have a constant over here. So as temperature goes up, in order to keep this side constant, the wavelength has to go down. So this shows that the object will change color from red to orange to blue, and then finally to white. And basically what white is, all wavelengths are present in high intensity in the visible spectrum. So it's not infrared, it's not ultraviolet, it's stuff that we can see. Time for a graph. There is a lot going on this slide, so let's take this one slow. What we're showing here are blackbody radiation curves for a black body at 3 different temperatures. And let me highlight that. See this red line right here? That's when the black body's temperature is 3000 Kelvin. Over here, that's when the black body is at 4000 Kelvin. And this blue curve here is at 5000 Kelvin. So let's see what else we have. Over here we have the wavelength in micrometers. So if you look at this point here, 1 micrometer, that's about 1,000 it's exactly 1,000 nanometers. So that's a little above the color red. So you're in the infrared spectrum here. As you move down, this little band here, let's see if I can just put a horizontal line on it. This is the visible light band. Okay, we start from red here, orange, yellow, blue, green, violet. What else can we show? Here's the intensity. This is how strong the light is. So the higher the curve, the more intense the light is at that particular wavelength. So another way of saying that, the x-axis plots the wavelength of the light emitted from the black body, and the y-axis shows how strong it is. We have one more line over here, this black line. This is a theoretical line. This is what classical theory, again, a theory before 20th century modern physics, shows what should happen to the blackbody radiation. More on that later. Let's break these curves down into a couple segments for a better understanding. The red, green, and blue curves are actually measured data that was done in a lab. This black line is what classical theory said would happen to the color of the light at 5000 K. So notice, here's the measured data, 5000 K. Here's what the theory said it should be. Now, just look at the blue, the green, and the red curves here. As the object heats up, as it goes from 3000 to 4000 to 5000 K, what happens to the light emitted?
The peak intensity of the light shifts from the longer wavelengths down to the visible spectrum where it starts as red light. So let's just pause a second here. Here's our longer wavelengths over here. Here's our shorter wavelengths. So we're shifting from longer to shorter. And here's our visible spectrum right over here. And that would be red over here. And then over on the left side, you would have what? Indigo, blue, etc. So this curve down here, you're peaking where mostly reds are visible. Then as you increase the temperature over to 4000 Kelvin, you can see the peak is shifting left, okay? And that's going to be our red, orange, yellow peak. Then at 5000 K, that's the blue curve, you've now shifted the peak more to the left, so all the colors are present. And what happens when you get all the colors present? You get white light. But now look at the classical theory prediction. As the wavelength decreases, intensity is going up here. It's going up tremendously, up to infinity. But your measured data, these are the blue curve, the green curve, and the red curves. Doesn't match very well, does it? It matches okay out here at the longer wavelengths. So the classical theory shows that the intensity of the emitted radiation approaches infinity as the wavelength gets shorter. Remember, wavelengths getting shorter in that direction. But that's not what happens. Shorter wavelengths means the light is moving into the ultraviolet end of the spectrum. Hence, this was dramatically named the ultraviolet catastrophe.
Because of this tremendous discrepancy between existing physics theory and reality, and remember, when you have a theory, no matter how good, no matter how elegant, and you have reality, reality always wins. So a new theory that wasn't quite understood very well, and it was quite revolutionary, was required. The wave theory of light could not explain the way the black body glows depending upon its temperature. And remember, that's called its spectrum. So in 1900, Max Planck made his brilliant assumption that atoms do not emit electromagnetic radiation, that is light, with any continuous value. They could only emit it in multiples of small, distinct amounts of energy, and this was named quanta. These quantum amounts are given by the following formula. The energy that's allowed, is equal to h, which is Planck's constant, and f, which is the frequency of the light. Now Planck's constant is very, very tiny. H is 6.63 times 10 to the minus 34th joule seconds. As hard as this hypothesis is for us to believe, Max Planck didn't like it either. He didn't believe it was real. It just worked. It's kind of like when you're doing homework problems and you're working from the answers in the book. You'll get something that works, but you have no idea why unless you work the problem yourself before you look for the answer. It just didn't make sense that atoms could have only steps of energy. Why couldn't they have any energy? For example, what this is telling us is that if you're trying to get a box from here to here, there's no way you can do it by just sliding it along the incline, because the energy here changes pretty continuously, at least in the macro level that we deal with a box in an incline. It says the box actually has to go upstairs. All right, this isn't the greatest analogy, but hopefully it points out what's going on here, that the energies of light that's being emitted from the atom can only do it in a stepwise function here. It can't be continuous. So Planck thought a real solution would someday be found. However, this one worked for some reason, so he went with it. Planck continued his analysis to try and make h equal to 0, to make it go away. If he could show that, he could get rid of this notion of quantized energy levels, and you could have any energy you want. However, he did not succeed. Didn't work. It turns out h is a fundamental constant of the universe we live in. Numerous measurements made by numerous other physicists confirm that this number was real and the energies were quantized. This is now going to lead us to another mystery of the physical world, and that's going to be worked on by Albert Einstein. And it uses the quantum theory. It uses Max Planck's quantum theory. It's called the photoelectric effect, and that's coming up next.
What is the energy of a photon with a frequency of 5 × 10 to the 18th hertz? We write the given, which is the frequency, and then right here is Planck's constant. And you don't have to memorize that. That will be on your formula sheets. So the photon energy equation is E is equal to HF. Substitute in the givens. We have Planck's constant. Here's our frequency. And we get 3.32 × 10 to the minus 15th joules, because seconds here cancels out with hertz, right? Because hertz is another way of saying 1/seconds. A photon has an energy of 4.2 × 10 to the minus 19th joules. What is the photon's wavelength? We write the energy we've been given, and since it's in joules, we'll use this version of Planck's constant, and we're going to need the speed of light, which we'll see shortly. We're going to combine the energy equation with the speed of light equation, where the speed of light is frequency times wavelength. So here's the energy equation here. We solve this one for frequency. So F is equal to C over lambda. We divide both sides of that equation by lambda. We can now plug this value of F right over there. So we get E is equal to HC over lambda. Now we're trying to find the wavelength. So we cross multiply the E and the lambda. The lambda comes up on top. E goes on the bottom on the other side. And now we just have to substitute in our givens. Here's Planck's constant, speed of light. Here's the given energy. And we get 4.74 × 10 to the minus 7 meters. Or we can write that as nanometers. Visible light is typically written in nanometers. So you move the decimal point over 2 spaces to the right, which decreases this by 2. So it goes from 10 to the minus 7 to 10 to the minus 9. And 10 to the minus 9 is nanometers. So either one of these answers would be absolutely correct. What is the energy of a photon with a wavelength of 750 nanometers? We have our given here, and we have to convert that to meters. So a nanometer is 10 to the minus 9th meters. Here's Planck's constant, and here's the speed of light. And we use our energy of light equation that we actually derived on the previous problem. The energy is hc over lambda. We substitute in our givens. There's Planck's constant. Here's the speed of light. Here's our given wavelength written in meters. And we get an energy of 2.65 × 10 to the minus 19th joules. What is the frequency of a photon with an energy of 4.5 × 10 to the minus 18th joules? The given is the energy. And here's Planck's constant, and once again we use the one with joule seconds because our given energy is in joules. Use the energy of light equation, E is equal to HF. Solve for F by dividing both sides by Planck's constant. We have our energy here. Here's Planck's constant, and hopefully you can see how the joules cancel out. And we're left with 6.79 × 10 to the 15th hertz.